Good day. I am a senior lecturer at the Department of Intelligent Cybernetic Systems at the National Aviation University. In this presentation, I will present the solution for monitoring the condition of rotating equipment as part of the task assigned by Mr. Eric. Our task was to create a system for classifying the condition of equipment based on vibration data. As Mr. Eric mentioned, the use of vibration signals to detect defects is beneficial across various industries. For our research, we received 158 files containing vibration signal measurements, which represent one-dimensional arrays of vibration data. We also received a file with labels that classify the data into two categories, functional and defective. It was decided to use heat maps to detect anomalies and patterns in the vibration signals that might not be obvious when working with numerical arrays. This approach also allowed us to apply the latest version of the YOLO 11 neural network from Ultralytic, which provides state-of-the-art results in image classification. For training, the dataset was divided into three parts. The first 1,000 heat maps were split into 80% for the training set and 20% for the validation set. The remaining 158 heat maps were allocated to the test set to evaluate the model's performance on unseen data. Next, I will visually demonstrate the entire process from training to using the final model. We will skip all the technical setup of the Python environment, CUDA installation, and necessary libraries, and move directly to the training process. Since we are using the transfer learning method, we will only configure the number of epochs, setting a small value to quickly see the results. Here, you can review all the settings that have been configured, along with detailed information about the structure of the neural network. This includes parameters such as the number of layers, the size of each layer, activation functions, and other key components essential for model training and performance. As we can see, the model has successfully completed its training and achieved 100% accuracy. The final result shows that the model has reached top 1 accuracy of 100%, indicating perfect classification performance. This confirms that the model effectively distinguished between the categories in the dataset. Next, let's move on to the results and write the code that will perform inference on each heat map individually. The first thing we can notice is that data augmentation was applied when creating the training batches. Additionally, upon analyzing the graphs, it becomes clear that the task of classifying the heat maps is relatively simple for this model. The convergence occurs very quickly, indicating that the model learns the patterns efficiently. So, let's load our newly trained model and execute the code to evaluate how it performs on each individual image. Now I will go through the images, and in the upper left corner, you will see the classification result. You can check the true class of each heat map in the corresponding file. A value of 0 indicates an intact state, while a value of 1 indicates broken. I am switching through the images, and as you can see, the classification happens almost instantly and with 100% accuracy. The 9th heat map corresponds to the broken class, and as we can observe, the prediction is indeed correct. In conclusion, the developed classification system using YOLO 11 and heat maps has proven to be highly effective for equipment condition monitoring. The model achieved 100% accuracy, demonstrating its ability to accurately differentiate between intact and broken states of equipment based on vibration data. This approach simplifies the data processing pipeline while providing real-time analysis capabilities. Thank you for your attention. I appreciate your time and interest in this presentation.